2 videos ago, we started studying probability spaces by looking at the sample space omega. There, we learned that the sample space is simply the set of all possible outcomes of an experiment. Then, in the last video, we explored measures, and in particular, probability measures, and we saw that their defining property is sigma additivity, which we could motivate through examples from everyday life. This led us to the definition of probability measures as normalized sigma additive functions mapping from a sigma algebra to the extended real numbers. But there's still one big question we haven't answered. Why do we actually need a sigma algebra in the first place? Why can't we just take the power set of omega? And more fundamentally, what is a sigma algebra? That's exactly what we're going to answer in this video, which is divided into 2 parts. First, we'll take a geometric perspective and see why using the power set doesn't always work, such that we need a different structure, and this will involve many big and small cubes and a few spheres. Second, we'll build an intuitive understanding of why sigma algebras are the right structure to work with in probability theory, and since we approach this part from the perspective of logic, this will involve a few foundational logical operations. Let's say we want to measure the volume of objects in 3-dimensional space in R3. Let's call this measure vol, short for volume. If we plug an object into this measure, it should give us a number, the number we intuitively think of as its volume. So for example, if we insert the sphere, we would like to have the number that we can also calculate with the well-known formula. How can we define this measure in such a way that it actually coincides with the intuitive notion of the volume of an object? What properties do we need? If you have watched the last video, you know that the definition of a general measure basically only needs 2 properties, one of which is sigma additivity. To capture the idea of physical volume, we need just 2 additional properties. First, the unit cube should have volume 1, and second, our measure should be invariant under rigid motions, meaning that if we shift or rotate an object, its volume stays the same. If you're wondering how this can be enough, let me give you an intuition. Notice that since we can shift objects around without changing their measure, we can actually determine the volume of smaller cubes than the unit cube. If we split the unit cube evenly into n disjoint small cubes, we know from the sigma additivity of our measure that the volume of the unit cube is simply the sum of the volumes of the small cubes. And since these small cubes all have the same shape, we can conclude that the sum is actually the same as n times the volume of one of the small cubes. So by rearranging, we know that the volume of each small cube is simply 1 over n times the volume of the unit cube. Knowing this, we can now go and approximate the shape of arbitrary objects by shifting appropriately small cubes to the appropriate places. And since we know the volume of each small cube, we can approximate the volume of these more complex objects by simply counting cubes. So let's say our sphere has a radius of 1. In this case, the volume is something like 4.189. Then we could start to approximate the sphere with a cube of side length 2, which yields the quite bad approximation of the volume by 8. To refine this approximation, we could split each side of the cube into 3 and only keep the cubes whose midpoint lies inside the sphere. Like this, we approximate the sphere by 19 cubes of volume 2/3 to the 3, which is something like 5.6. And if you continue this process, our arrangement of small cubes approximates the shape of the sphere increasingly good and therefore also the volume, even if it's not monotonically getting better. So far, everything sounds consistent. But now comes the big question. Does such a measure actually exist? For non-mathematicians, that might sound a bit weird, but this is actually very important, as we shall see. Because this question was answered in the early 20th century by two very famous mathematicians, namely Banach and Tarski, and the short answer is no, such a measure does not exist, at least not on the whole power set. What they proved is the following. If we have two sets, A and B, in the space Rn, that have a non-empty interior, then we can find countably many other sets, Ck, and rigid body transformations Tk, such that we can get the set A as a disjoint union of the set Ck, and if we simply shift these sets with the transformations Tk, we can get the set B as a disjoint union. If you cannot directly see why this is a big problem for our measure, don't worry, you will see it in a second. The theorem starts with basically arbitrary sets A and B. So let's go back to our sphere with radius 1 and take it as a candidate for set A. And as set B, we simply take our cube with side length 2. Then we know from before that these two do not have the same volume. So to go on, the theorem by Banach and Tarski then tells us that there are many sets Ck such that we can represent the set A, our sphere, as a disjoint union of these sets. And additionally, the theorem tells us that we can shift and rotate these sets in such a way that we can also represent the set B, our cube, as a disjoint union of these sets. And this is a big problem, because then we get the following chain of equalities. By the Banach-Tarski theorem, we know that the volume of the sphere is the same as the volume of the union of these sets. But since they are disjoint, we know from the definition of a measure that this is simply the sum of the volumes of these sets. Then, since our measure is invariant to rigid body transformations, each of these volumes does not change if we shift them around in space. But since these shifted sets are still disjoint, we can again use the sigma additivity of our measure to conclude that this is the same as the volume of the union of these shifted sets. And by the Banach-Tarski theorem, we know that this union is simply our cube. So we would conclude that the volume of our sphere is indeed the same as the volume of our cube. And that's bad, because we know intuitively that these volumes are not the same, but at the same time, the theorem by Banach and Tarski is mathematically proven. That is, it follows from strict logic. And this is also what makes it a paradox. It is a true statement, but intuitively it seems so wrong. And it does feel so wrong because we can only imagine sets that are reasonably well behaved, and the sets from the Banach-Tarski theorem are unimaginably complex. So you simply cannot imagine them in your head. So what do we learn from this? We learn from this that there are sets so strange that we can't assign them an intuitive volume in a consistent way. In other words, we can't define our measurable on the entire power set. In this second part, I want to look at sigma-algebras from the perspective of logic. That might sound a bit strange at first, but don't worry, it will make sense by the end. To get the idea of where this might come from, we first have to realize that probabilistic reasoning can be considered as an extension to strict logical reasoning in at least two ways. First, in terms of uncertainty. So, if we have a logical statement A, it can be either false or true, which we can represent by the numbers 0 and 1. Probability theory extends this idea by allowing every value in between. The statement A can be almost surely false, very unlikely, somewhat likely, highly likely, or almost surely true. So instead of only allowing for black and white, we now have a whole spectrum of gray in between. The second way how probability theory is an extension to logic is in terms of hypotheses, that is, when you need to think about causes and effects. Mathematically, if the logical implication A implies B is correct, then we know that if A is true, also B is true. And likewise, if B is not true, you know that A is not true. For example, if a disease always causes a certain symptom, and we observe a person with the disease, we know she has the symptom. And likewise, if we observe someone without that symptom, we can safely conclude they don't have the disease. But if we do observe the symptom, logic alone can't tell us whether the disease is present or not. That's where probability theory comes in. It allows us to reason in both directions using conditional probabilities. If we know that A is true, we can consider the conditional probability of B given A, and if we know that B is true, we can simply consider the conditional probability of A given B. So, why do I tell you about all this? Since probabilistic reasoning can be seen as an extension to logical reasoning, but probability measures are defined on sets, we have to translate the operations of logic into operations between sets. And the idea behind sigma-algebras is simply to make sure that this translation is consistent, so we can reason about uncertainty just as logically as we reason about truth. So, what are the basic logical operations that we need? First of all, we need to be able to make statements at all. That means that there should be any statements to which we can actually assign a truth value. The easiest ones here are the tautology and the contradiction. That is, the statement that is always true and the statement that is always false. Secondly, there are basically only three logical operations that you need to build a complete logical system. And these are the negation, the conjunction, and the disjunction. So the logical not, the logical and the logical or. And we will now go and simply translate these operations to operations between sets and find the definition of a sigma-algebra. Let's start with the tautology. In terms of logic, this is a statement that is always true. So if we translate it into subsets of the sample space, we get a set that contains every possible outcome. That is simply the whole sample space. That means omega should be measurable. And if you'd like, you can also play the same game with the contradiction. In terms of logic, this is a statement that is always false. That is, if you translate it into a set, it should contain not a single outcome. And that means that the empty set should be measurable too. So, for a collection of sets to qualify as a sigma-algebra, it has to contain the whole space and the empty set. Okay, so let's look at the negation. In terms of logic, the negation of a statement A always gives you the opposite of A. That is, if A is true, then negative A is false and vice versa. If we translate this into sets, then the negation is simply the complement. If an outcome omega is contained in a set A, then by definition omega is not in the complement of A and vice versa. And there's even more analogy here. since we know that capital omega is the disjoint union of A and the complement of A, so either A or negative A is always true, and we already know that omega is measurable and has a probability of 1, then we know that if A is measurable and has a probability of P of A, then we directly get that the complement should have a probability of 1 minus P of A. And to be able to assign this value, we need the complement of A to be measurable as well. So for a collection of sets to qualify as a sigma algebra, we need that whenever a set A is measurable, its complement is measurable too. Lastly, let's have a look at conjunction and disjunction. In terms of logic, if we have two statements A and B and both are true, then we know that the conjunction of A and B, the logical AND, is also true. In terms of sets, this simply is the intersection. If an outcome omega lies in A and omega lies in B, then it lies in their intersection. Likewise, if at least one of A and B is true, then the disjunction of A and B, the logical OR, is also true. And in terms of sets, this is simply the union. If an outcome lies in at least one of A and B, then it also lies in the union of A and B. So if we have two measurable sets, A and B, we know which elements are contained in them and how much probability we should assign to them. So we can also look at their union and their intersection and assign a corresponding probability to them, which means that they also need to be measurable. So far, we can combine finitely many sets, but we also need to handle countably many sets because we want to reason about sequences and limits. For example, if we toss a coin repeatedly, we want to ask, what's the probability that I'll eventually get at least one head? To make such questions meaningful, our system also needs to be closed under countable unions and intersections. So to summarize, for a collection of sets to qualify as a sigma algebra, we need to ensure that if a sequence of sets AN is measurable, then their union and their intersection should also be measurable. And that's the definition of a sigma algebra. It's essentially logic translated into sets, allowing us to extend logical reasoning into the world of probability. So in a sense, sigma algebras are what makes uncertainty logical. And with that, we're at the end of this video. I hope you liked it. I hope you could learn something from it. And thanks for watching.